In this video, I will show you how we can make simplifying approximations when performing equilibrium calculations. This content comes from Chapter 14.8. The first thing we'll do is cover how when k, the equilibrium constant, is very small, we can assume x is small. This comes from the content in slide 17 of the lecture notes. Second, we'll cover what happens when k is very large. When can we assume that x is small? This comes from slide 18. Finally, we will look at how we can use successive approximations when our assumptions fail. First, we can say that when k is very small, the reaction will favor reactants. When the reaction favors reactants, very little of A will be converted to B as equilibrium is established. Therefore, when we use our ICE table for a given reaction, we will find that the amount of loss from our initial value, in minus 2x in this example, will be very small. So we can then assume that this is so small that we will ignore it. It is important to note, however, that we cannot ignore this x, as this value must be a real value and not 0 that we started with. Let's do an example. In this example, we have a reaction where the k is a very small value. Initially, we are told that we have minus 2.5 molar H2S. This isn't a concentration, but note that we are using the Kc. The first thing you will note is that we have no concentration of our two products. We know from this, without doing any calculation for our Q, that our reaction will proceed in the forward direction. But because our K is so small, whatever change will occur will likely have very little effect on this initial concentration of H2S gas. So initially, we'll complete our ICE table. We say that we'll lose 2x and gain 2x and 1x, so that our equilibrium concentrations are 0.25 molar minus 2x, 2x, and x. We can then write our equilibrium expression, our concentration of H2 gas first, or 2x squared times our concentration of S2 gas divided by 0.25 minus 2x. If you'll note, if we went on to solve this problem, we would have a big problem, namely that we are going to have x cubed. And that would be a pretty hard problem to solve, a trinomial solving for x. This x cubed is not a problem if we have no other x's on our equation. So it would be really nice if we can assume that this 2x is small. And given that our k is so small, and that the change we expect is therefore going to be small as well, we'll go ahead and do that. We're going to assume that this is small. And I'm going to put a little asterisk there to remind myself to go back and check this approximation. If we go ahead and solve this problem, we'll come up with 4x cubed in the numerator divided by, sorry, I forgot my squared units here, given our coefficient, and 0.25 squared in the denominator. Again, we've ignored that minus 2x. And this is all equal to our equilibrium constant. When we multiply both sides by 0.25 squared, we can then divide by 4 on both sides of the equation. And finally, take the cube root. Sorry. 1.67 times 10 to the minus 7, 0.25 squared divided by 4, take the cube root. This should give us our value of x. And when we calculate this, we find that the value of x is 0.001377. If we look at this value, we can check whether or not our approximation initially was a valid one. We start off with 0.25 molar, subtract our 2x, gives us a value within our significant digits, which is still 0.25 molar. Our approximation is valid because within significant digits of our original answer, we still get 0.25 molar. Solving for our other concentrations, so 0.25 is our concentration of H2S gas. We find that H2 gas has a concentration of 2 times 0.001377 molar, and this S2 gas has a concentration of 0.001377 molar. And the significant digits here, given our initial value, will be in this place. So you have 0.0014 molar for S2 gas and 0.0028 molar for H2 gas. There's our answer. So, to recap, when K is very small, the reaction will favor the reactants, and therefore we can make an approximation that this initial value will not be modified significantly. By getting rid of this 2x, we greatly simplify the math that we have to do to solve for x, and we can check our answer by seeing whether that initial assumption that this is a very small value gives us indeed a number which did not change from the original value. Now, when K is very large, the situation is a bit different. In this problem, we have a copper ion and a certain amount of ammonia that is added to this solution. Sorry, this should read aqueous. This is a solution. And our K for this reaction is very large, meaning products are highly favored. So, initially, we have no products, and we can expect that this reaction will go nearly to completion. In fact, that is the approximation that we are going to start off with. When K is very large for a given reaction, the equilibrium will favor products. We will assume initially that the reaction does go to completion all the way to those products as a limiting reagent problem. And then we'll run the reaction in reverse to determine the equilibrium concentrations. This will allow us to assume that at equilibrium, the concentration of our products is roughly equal to what we started with. This value here, the modification of those product concentrations, when we establish equilibrium, should be very small if K is very large. We'll make this approximation, we'll solve it, and then we'll go on and check the approximation. So the first step, if you recall, is to assume the reaction goes to completion. So we are going to modify our ice table, and maybe we should call it a nice table, because we are going to solve a new set of initial concentrations. Please note that there are out in front of this ammonia, so there's going to be 4 times as much of this consumed for every one of these. All right, so our new initial concentrations, we assume all of this copper is going to be consumed to form products. That is our limiting reagent. Now, by inspection, I determine that. You may have to calculate this in the future. If I consume all of my copper, I should have none left. And 4 times this amount that we subtracted will be removed from our NH3 concentration, which is a value of 0.03. So we have 0.003, sorry, 0.097 molar. Okay, with these values, we can now solve the equilibrium ice table just like we used to, only now this is a nice table. Since we now have products and we have no reactant here left, the reaction is going to go in reverse. That was the second step. We're going to run this reaction in reverse. So we're going to lose 1x here, gain 4x here, and gain x here. Our equilibrium concentrations will be x 0.097 molar plus 4x, and 7.5 times 10 to the minus 4 molar minus x. Putting this into the equilibrium expression, Kc equals our products, 7.5 times 10 to the minus 4 molar minus x, all over copper times the amount of ammonia we'll have, 0.097 molar plus 4x. This is to the 4th. Solving for x in this equation would be incredibly difficult. We will have x to the 5th, a crazy large polynomial. Here, making the assumption that x is small, that the products are so highly favored that any loss here is going to be small, and any gain we have on the reactant side will be small as well, because the reaction favors products so heavily. So again, I'm going to put a little asterisk here, and this is our assumption that we're going to need to come back and check to make sure both of those are true. Now our expression reads 7.5 times 10 to the minus 4 divided by x. Now notice I did not ignore this x because this is a real value. 0, it's no longer 0. It needs to be a real number. I can't ignore that x. 0.097 to the 4th. I'm going to skip over a bit of the algebra now and just jump to the conclusion, which is that x will equal 4.983 times 10, ready for this, times negative 13. This will be a molar concentration. Our significant digits here, there were 2 in our problem, so we'll leave that. This is indeed a very small number, and if we look at our values up here, we don't even need to really calculate them. This is so small that it will make no difference in those initial values we had. We will find that this value equals our copper 2+ concentration without modification. And we can go back and calculate our ammonia concentrations, which are still 0.97 molar equals a concentration of ammonia, and 7.5 times 10 to the minus 14 molar equals a concentration of copper ammonium complex. Oops, that's a 3, that's a 4. And there are our answers. All right. That is an example where K is very large. What happens if we go back and check and find out that our approximations weren't very good. We have several options. The first is we could just go through and solve for x like we normally would. Note here that that would be incredibly difficult. I don't know how to solve a polynomial of the fifth order. I'm guessing that you don't either. So we do have another option, and let me show you how to do that, and that is to use successive approximations. Let's run through an example where this is going to be necessary. So we have an example here where we have a k which is pretty small. And we have some initial values of our two gases. So this is N2 gas reacting with 3 hydrogen gas to form ammonia gas. This is our Haber process we've talked about. So we have no ammonia to begin with. And we can set up our ice table. We have no products, and this reaction is going to favor reactants because our K is so small. I should say this is the Kp. So we are going to lose 1x here, 3x here, and gain 2x. So our equilibrium concentrations, or pressures, sorry, 0.200 minus x, 2 minus 3x, and 2x. We put this into the equilibrium expression, Kp equals 2x squared over 0.200 minus x times 2 minus 3x cubed for the coefficient on the hydrogen. This equals our equilibrium constant. Here, we might want to assume that because K is so small, that the x is small. So let's go ahead and do that. We're going to say that this is small, and this is small. Because reactants are favored, the loss of our initial reactant pressures, we might assume, are going to be small as well. But we need to go back and we need to check that. When we solve this problem now, we have 1.45 times 10 to the minus 5th equals 4x squared, 0.200 times 2 cubed. And I'll jump right to the punchline here that x, when we solve for it, equals 0.002408. This is units of atmospheres. I don't know if you can notice already we have a problem. Our significant digit in these initial values, this initial value here, I didn't give any significant digits up here, I probably should have, but 0.200 is in the thousandths place. And we have a change in x, which occurs in the thousandths place, which means our assumption that x is small didn't work. Indeed, when we calculate the partial pressure of N2, we have 0.200 minus 0.002408, and our value equals 0.19759, where our number has indeed changed. Likewise, we can see what happens to hydrogen gas, and we see that a value of 2.00 subtract 3 times 0.002408 equals 1.9927 ATM. Again, we have a change in the value, which is significant. So what can we do? I don't really want to go back and solve something that is going to be x to the third, another x, that's x to the fourth. This is going to be a really hairy algebra. But we have another choice. We notice that these values here, we can use them back above. We assume that x is small. We know that's not true, but we can take these values and we can plug them into this equation up here. Rather than assuming x is small, let's just use the new values we calculated. So this is a first step in approximation. There's our second step. All right, so we are going to take those values and we are going to say 1.45 times 10 to the minus 5 equals 4x squared over 0.19759 times 1.9927 cubed. And I'm carrying lots of significant digits along to make sure I don't have any rounding errors as I move forward. We can calculate x again using these values, and we find that x equals 0.002381. The value is slightly different than our value above, but we still have a value change here. So let's take a look at what happens to our PN2 pressure, and we subtract our x from 0.2, we get 0.1976, and pressure of hydrogen is equal to 1.9928. These are in atmospheres. These values are actually pretty much the same as what we had above. They would round to the same numbers. But recall that x is actually the concentration, or 2x is going to give us the concentration, our pressure of NH3 gas in this problem. And because of that, this value is changing. We want to do at least one more step. So let's take a look. Let's do a third step here. So we're going to take the values we calculated here and put it back into this reaction. 1.45 times 10 to the minus 5th. And we're going to keep on doing this until our values stop changing. And I'll give you a hint, this will be the last time. 0.1976 times 1.9928 cubed. And when we calculate the value of x, we find that the value of x is 0.0023811. And that value has not changed at all from the value above. So for our final concentrations, the pressure of ammonia is 0.00476 atmospheres. The pressure of N2 remain the same, again, 0.19. We round it up, it's 8 atmospheres. And the pressure of H2 is the same as above, it's 1.99 atm. So we can see that when our assumptions fail, as they did here, we had a change in value, we can go back and take these values which we just calculated and plug them back in as a second step of approximation. Those values give us a better answer for x, and if we still are not quite at a stable value, we can try one more time. And we keep on doing this until the value of x does not change or our pressures and concentrations do not change. Once we've done that, we know we have converged on an answer through a process of successive approximations. Okay, that concludes this video where we have discussed, let me get my piece of paper here, simplifying approximations in equilibrium calculations. We dealt with when k is very small, when k is very large, and finally using successive approximations. There are more resources on Clio, so please check it out. Thank you.